All right, today we are tackling a big one. It's one of the most famous and, let's be honest, sometimes feared problems in the coding world, trapping rainwater. It's an absolute classic for a reason, and by the end of this, you're going to see just how beautiful its solution really is.
Okay, so let's just jump right in. Forget about code for a minute and just look at this as a puzzle. You've got this map, right? A bunch of bars with different heights. Now, if it started pouring rain, where would the water actually get stuck? And more importantly, how much water would we be talking about in total?
So that's our mission, plain and simple. We're given a set of numbers that represent this map, and our job is to figure out the total amount of water that gets trapped between all these bars. We've got to count every single drop. And to make sure we're all on the same page, this is the exact array we're going to be using for this whole breakdown. Each of these numbers corresponds to one of those black bars you just saw. So what's the magic number we're aiming for? For this particular map, the answer is 6. Go ahead and burn that number into your brain. Whatever solution we come up with, it has to end up at 6. So how on earth do we even begin to calculate this? Well, the core idea is actually pretty intuitive. For any given spot on our map, the amount of water it can hold is all about the walls on either side. Think about it. You need a wall to your left and a wall to your right to form a container. And the water level can only rise as high as the shorter of those two walls. From there, you just subtract the height of the ground you're standing on, and that's your water depth. Simple as that. Okay, so with that rule in our back pocket, let's talk about the first solution that probably pops into most people's heads. This is the brute force approach. It's the most straightforward, direct way to think about the problem. The logic goes something like this. You go to the first bar, you stop, you look all the way to its left and find the tallest bar there. Then you look all the way to its right and find the tallest bar there. You take the shorter of those two, apply our formula, and you've got the water for that one spot. Okay, great. Now, move to the next bar and do that whole scan left, scan right thing all over again, and again, for every single bar. And that right there is the big catch. This method isn't wrong, not at all. It will absolutely give you the correct answer. But my gosh, think about how much work that is. All that constant re-scanning of the same areas over and over, it's just painfully inefficient. This leads us to the million-dollar question. There has to be a better way, right? Can we possibly figure this out without doing all that repetitive scanning? Is there some trick to finding those left and right maximums more efficiently? And the answer is a resounding yes. This is where we get to the really cool part, the aha moment. It's an elegant, beautiful solution called the two-pointer technique, and it completely changes the game. I mean, just look at this comparison. It's night and day. The brute force approach is O of n squared. That means as the map gets bigger, the time it takes to solve gets way, way worse. But the two-pointer trick, it's O of n. It just makes one single pass through the array. This isn't just an improvement, it's a massive leap forward. And what's really neat is they both use the same amount of extra memory, which is basically none. So how does this magic trick work? Well, the setup couldn't be simpler. You put one pointer at the very start of the array and another one at the very end. We'll also keep two little variables to remember the tallest wall we've seen from the left so far and the tallest from the right. Then these two pointers just start walking towards each other. And this right here, this is the golden ticket, the key insight that makes the whole thing click. Remember how the water level is always limited by the shorter wall? This method uses that to its advantage. If we know our tallest wall on the left is, say, a height of 5, and the tallest on the right is an 8, then the left wall is our bottleneck. That's what limits the water level. We don't even need to know the exact details of what's happening way over on the right side to make a calculation on the left. Okay, that's enough theory. Talk is cheap. The best way to really wrap your head around this is to see it in action. So let's do a step-by-step walkthrough and watch how this thing actually builds our answer.
All right, here's our starting line. Our left pointer is at the beginning, our right pointer is at the end, our left and right maxes are at 0. And of course, our total water is 0. We haven't done anything yet.
So, first things first, we compare the height where our pointers are. On the left, at index 0, the height is 0. On the right, at index 11, the height is 1. Since the left side is shorter, that's where our attention goes. We're going to process from the left. So, we move our left pointer one step to the right, to index 1. The height here is 1. Now, since this is taller than our current left max of 0, this becomes our new tallest wall on the left. So we just update left max to 1. You can't trap water on top of a wall, so our water total is still 0. Okay, we move the left pointer again to index 2. The height here is 0. Now, this is interesting. This height is less than our left max of 1. That means we found a little dip. We can finally trap some water here. And the math is super simple. It's just our left max minus the height of the current bar we're on. So that's 1 minus 0, which gives us 1 unit of water. And just like that, our total trapped water is now 1. We're on the board. Now, you can imagine how this little dance continues. The pointers keep moving inward, calculating water whenever they find a dip. Eventually, the right side might become the shorter boundary, and then the right pointer would start doing the work. If we followed this all the way through, we'd get to our answer of 6. So let's just step back and really appreciate why this is so much better. And the payoff is just so clear when you see the numbers side by side. By ditching those nested loops, we go from quadratic time to linear time. For a huge dataset, that's the difference between a program that finishes in a blink and one that could take, well, a very, very long time. The secret sauce is that single pass. It's so clever. By having our pointers work from the outside in, we guarantee that every single bar on that map gets looked at and processed exactly one time. There's no repeated work, no wasted cycles. It's just pure, clean efficiency. So we did it. We cracked trapping rainwater. But this two-pointer trick, it's more than just a solution to one problem. It's a whole way of thinking. And it leaves you with a really cool question to ponder. How many other problems out there seem super complicated on the surface? Problems that look like they need some slow, brute force solution, but are really just waiting for a clever, elegant approach like this one to unlock them?